Today we are again talking about discrete systems with 1 degree of freedom. We are still talking about the eigenbehavior and especially looking at how to solve the ordinary differential equation system using Simulink. So again, the example is the model of vertical dynamics of a car, the very simple 1 degree of freedom model with a mass, with a spring and the damping factor. And we are also dealing with a well-known differential equation, and we will show how Simulink helps us in modeling this system. In fact, what we have to do is to look at the equation as we have derived it already in order to find the state space representation. So we have solved the equation for x double dot, and now we can model this equation within Simulink, and we start with a line which is the signal representing x double dot. And obviously if we have x double dot, we need to place two integrators on our sheet in order to come up with x and x dot. So this is the first integrator. Input to the integrator is x double dot, output is x dot, and the output x dot from the first integrator is then again the input to the second integrator where the output is x. So we have, so to say, the complete information about our variables x, x dot and x double dot, as you can see here. And of course all the integrators need to be fed by initial conditions, which means that the first integrator is fed by the initial condition with regards to the velocity, and the second integrator is representing the initial position of the system. Now we already have another block here on the very left, and that is the summation block that gives us the sum of the two addends that we see, or that should give us the sum of the two addends that we see here in the equation. And obviously for this task we need to first of all feed back x dot. So x dot needs to be fed back through a gain, and the gain, which you see here denoted by damping, is k over m. So k over m by x dot is the output of this gain, and then of course we need to look at the negative input here to this summation block, because we have to consider this negative sign in the equation. And now I guess you already know what will happen with the second addend here. There we have to feed back the signal x, and obviously this can be done by using another gain, and this gain is c over m. So it represents the stiffness of the system, and then what is fed back is the negative value here, because we need to consider this minus sign here. Now the question is, can we say a little bit more about the signals behind those gains? If we look at this signal, then obviously this signal is 2 times delta times x dot, and this signal is omega 0 square times x, as you know from the other version of this equation. Now of course if we want to run the system, we also want to know about the results. We need to look at the output of our simulation, and what you see now on this slide are two different possibilities how to look at that output. One possibility is to use a scope directly within Simulink, and we use two inputs to this scope. The first input shows the velocity, the second input here shows the position. Another way is to not only be able to look at the output within Simulink, but to bring the output to the workspace of Matlab, so that we might be able to do some more signal analysis with Matlab. And this is done first of all using this block, which feeds the two signals velocity and position onto a bus line, and then we are using this sim out block to bring the data to the workspace. And then in the following you will directly see how we can analyze the system and do different simulations within Simulink. Enjoy machine dynamics with MathWorks.